we're going to look at the limits as x goes to infinity of some trigonometric functions and some variations thereof. This first one, the limit as x goes to infinity of cosine of x, this one does not exist and is not equal to plus or minus infinity. And the reason, of course, is that this cosine function is a wave function and it oscillates between -1 and 1, and there's no horizontal asymptote of the form y equals L, so that the function gets closer and closer to this value L. So the limit simply does not exist. However, if I divide cosine by x, as x goes to infinity, this cosine stays between -1 and 1, but dividing by x makes the value, the absolute value, smaller and smaller. So we would expect this limit to be 0, and we can use the Squeeze theorem to prove that. So we have -1 is less than or equal to cosine of x for any x which is less than or equal to 1. And remember how this Squeeze theorem works. If I multiply across here by 1 over x, which is positive, I get -1 over x is less than or equal to cosine x over x, which is less than or equal to 1 over x. And now, of course, the limit as x approaches infinity of -1 over x is less than or equal to the limit as x approaches infinity of cosine of x over x, which is less than or equal to the limit as x approaches infinity of 1 over x. But we know this one equals 0, and we know this one equals 0, so this is squeezed between two functions which go to 0, so the limit is 0. So we have this limit is 0, and similarly we could show that the limit as x goes to infinity of sine of x over x is 0. And notice you shouldn't confuse that with the limit as x goes to 0 of sine of x over x, which is 1. Now what about this limit? We have as x approaches infinity, 1 over x is approaching 0, and we have x is approaching infinity, and we have two different forces acting on this function. The x is increasing, but the sine 1 over x is going to 0. So the question is, which of these two forces wins the battle? In fact, we can reshape this and use our old familiar limit, the limit as x goes to 0 of sine of x over x, to figure this out. So if we rewrite this as the limit as x goes to infinity of sine 1 over x over 1 over x, then if I say let y equal 1 over x, I have as x approaches infinity, y approaches 0. So this is equal to the limit as y goes to 0 of sine of y over y. And of course we know that this limit is 1. So we must be very careful with these limits. A lot of these functions look the same, but they behave very differently as x approaches infinity. And here, this is a mishmash of a rational function and a trigonometric function. Perhaps the best thing is to try our old trick and hope for the best, and divide by the highest power of x in the denominator. So this is the limit as x approaches negative infinity. I'm going to divide numerator and denominator by x squared and hope for the best. Breaking off this fraction, we get the limit as x goes to minus infinity of 5 over x plus 1 over x in the numerator divided by 1 plus sine of x over x squared minus 4 over x squared in the denominator. Now this is equal to, well, the numerator is going to 0, and the denominator is going to 1 plus the limit as x approaches negative infinity of 1 over x times sine of x over x, and this is going to 0. Well, the limit as x approaches negative infinity, 1 over x is going to 0, and sine of x over x is also going to 0 by the Squeeze theorem. So both of these are going to 0, so this limit is 0. So our limit is 0 over 1, which is 0, and we're done. Now what about the limit as x goes to infinity of sine 1 over x? Well, if I let y equals 1 over x, as x approaches infinity, y approaches 0. So this is the same as the limit as y goes to 0 of sine of y, and that's just 0.